Hello everyone. In this fifth tutorial of the series on fire and smoke with a fluid simulator in Blender 4.5, we'll take a look at some of the main domain parameters, specifically those in the settings, gas, fire, and collection sections. Among other things, some of these parameters will allow us to create flames and smoke that look livelier and less uniform. As mentioned in the introductory video of this series, the PDF version of this and other episodes is available for free download at the link you'll find in the description. Let's start with the main elements of the settings section. By now we're familiar with the resolution divisions parameter, and we know that if the size of the voxels shown by the small cube at the bottom of the domain is very small, while the domain itself is large, more calculations in memory will be required to run the simulation. The adaptive domain option, found at the bottom of the settings section, allows Blender to dynamically change the domain size during the simulation. Even with adaptive enabled, however, the domain will grow in height only up to a certain point. After that, the smoke will begin to disappear when it touches the ceiling of the domain, treating it as an outflow. It's possible to make the smoke dissolve more quickly with a dedicated option in the gas section, which we'll look at in a moment. But first, let's disable adaptive domain and take a look at the border collisions section. The border collisions parameters, when enabled, cause the sides of the bounding box to be treated as obstacles, deflecting flames and smoke, rather than as outflows, which is the default when they're disabled, meaning fire and smoke simply vanish instantly at the borders. By enabling border collision for the ceiling of the domain, the smoke will build up there, and as it spreads sideways, it will disappear when it reaches the edges, since border collision is disabled on the sides. Enabling border collision on the other sides as well makes the domain behave like a closed box, where fire and smoke continue to accumulate rather than dissipating on contact with the walls. Going back to the top of the settings panel, we find time scale and adaptive time steps. Time scale simply lets you slow down or speed up the simulation. The Adaptive Time Steps checkbox, which is enabled by default, lets the algorithm decide when to calculate more intermediate steps, called steps, for each frame of the animation. The three parameters located under this checkbox relate directly to the algorithm used to determine how many steps to perform each time. Maximum and minimum are self-explanatory, while CFL number is a bit more complex. Without going into implementation details, what we need to know is that a higher CFL number requires fewer steps and therefore less computation time, but the result will be less accurate. In simulations where flames and smoke move particularly fast, it's better to use a lower CFL number to improve the quality of the simulation. The gravity parameters are disabled by default because the global settings from the Scene tab are used. If you disable gravity globally in the Scene tab, these parameters become available again in physics and can be modified. Empty space works only with smoke elements. Specifically, voxels filled below this threshold will be considered empty and ignored in the simulation, saving computation time. Moving on to the gas section, we first find the buoyancy density and heat parameters, which represent the upward force on gases, the first based on gas density and the second on their temperature. These two values don't directly represent temperature and density, but rather the upward forces due to them. Fortunately, the tooltips for these parameters are very clear and explain that increasing these values makes gases rise faster. Buoyancy heat, in particular, is the upward force due to the heat of the smoke. The initial difference between the smoke temperature and the surrounding environment is defined for each inflow object using the initial temperature parameter. In the inflow object panel, we also find the density parameter, which is linked to the domain's buoyancy density. Vorticity controls the turbulence of the smoke, which will also indirectly affect the flames. The higher the vorticity value, the more disturbed the smoke will be. Be careful, because even low values for this parameter can create very intense turbulence. On screen, I'm also showing how the results vary with changes in buoyancy density, which makes the smoke rise faster. To prevent gases from accumulating on the ceiling, and in general to make them disappear more quickly, we can enable dissolve and adjust the dissolve time parameter, which is measured in frames. Naturally, the lower the dissolve time value, the faster the smoke will disappear, because it will remain visible for fewer frames. The dissolve slow option makes the gases dissolve logarithmically, that is, quickly at first and then more slowly over time. The gas section also includes noise and fire, which allow us to add disturbance to the flames. Noise, in particular, mostly affects the flame contours, adding lots of detail there, making it useful for creating, for example, a campfire or fireplace fire that looks more turbulent and less uniform. The strength and scale parameters intuitively control the intensity of the disturbance. The uppers factor parameter refers to an additional subdivision factor applied to the domain's base resolution, used to create noise details. This also explains why the simulation slows down, since the noisy regions are calculated at higher resolution. As for the parameters in the fire section, we immediately notice that there is also a vorticity parameter here, just like in the gas section. As with smoke, vorticity introduces turbulence, in this case to the flames. Flames also have a temperature, and as with smoke, higher values make them rise faster. Combining the two parameters results in taller, livelier flames. The collections section contains two fields where you can specify collections, called flow and effector. These allow you to include in the simulation only the flow and effector objects that belong to the specified collections, if any. Effectors are special elements that let you define objects capable of deflecting the path of fire and smoke. We'll cover the two types of effectors, colliders, and guides in a later episode. By default, no collections are specified, so all flow objects and all effector objects are taken into account in the simulation. That's it for this tutorial. In the next one, we'll look at the remaining domain parameters to complete our understanding of both domain and flow object settings, so that we can better control the appearance of fire and smoke in the simulation. If you enjoy my content, the best way to thank me is to subscribe to the channel and leave a like on the video. Thanks, and see you soon.